to section 8.2, applying exponent properties involving quotients. We're going to work with the division rules today, and we have the quotient of powers property. And what this is saying to you is that you have the same base that are being divided, and you get to subtract their exponents. It has to be the one in the numerator minus the one in the denominator. That's the order that has to be done. The one in the numerator minus the one in the denominator. And we say here that A cannot equal 0. Why do I have to say A cannot be 0? Any thoughts on that? Jack?
0 can't be divided and nothing can be divided by 0.
Okay, we can't divide by 0. We can't divide by 0. That is an undefined operation, dividing by 0. So let's look at this property with 6 to the 11th over 6 to the 5th. And what you should be thinking along the way is you should be thinking 6 to the 11 minus 5. That's what you should be thinking. 11 minus 5, class, is 6. So we're going to have 6 to the 6th power. I would expect you to go from that problem directly to the answer and write it, not to put down the thinking part of it. Angela?
When it says like 11 minus 5, it does mean like to the 6th part. It doesn't mean like 6 to the 11th minus just like 5.
No, no. It's 6 to the 11th power divided by 6 to the 5th power. And what we get to do is we get to subtract the exponents because of the following thing. When I was in high school, I didn't learn how to subtract the exponents. That's not how we were taught. Do you agree that 6 to the 11th, that's how it's written out, longhand? All that multiplication divided by 6 to the 5th, 5 of them on the bottom. Are we okay so far? I just wrote it out longhand. Now, you guys know that these two cancel, don't they? 6 divided by 6, 6 divided by 6, 6 divided by 6, 6 divided by 6, 6 divided by 6. These all cancel with each other. How many do I have left? 6 of them. That's what that exponent is telling you. When you subtract those, you're really doing that canceling. That's how I learned it, is canceling. But it's just a subtraction of the exponents. 11 minus that 5 leaves me with 6 6's in my numerator. Okay? And whatever I get for an answer, I got to write in the numerator. Okay? We'll talk about negative exponents another day, so I'll just remind you of that right now. Questions? Angela, does this kind of take care of what you were thinking about?
Yeah.
Okay, wonderful. So I have negative 4 to the 9th over negative 4 to the 2nd. We're dividing. Negative 4 to the 9th divided by negative 4 to the 2nd. I have a hint there with some parentheses. Okay, I've got a hint there with some parentheses. So what do you think this is going to look like here? What do you think, Rebecca?
Negative 4 to the 7th?
Yes, negative 4 to the 7th. That would help if I actually had a pen to write with. Let's try this again. Negative 4, and that's in parentheses, to the 7th. Now, just like Emily was asking about earlier, is that the same as negative 4 to the 7th like this? It will give the same answer, but when I write using exponents, then I would expect that negative 4 in parentheses. You're not simplifying it yet. You're just telling me, okay, I subtracted the exponents and this is what I got. I haven't done anything else. I'm not going to do anything else yet. Any questions there? Okay. All right, let's go on to the next one here. Let's do a little combining. We got 9 to the 4th times 9 to the 3rd all over 9 squared. Now, what does it tell you to do on top first? Think about that. What does it tell you to do on top first? Jordan? I'm multiplying. So what do I have to do to the exponents? Add them together. That's right. What is that going to be, Jordan?
9 to the 7th.
9 to the 7th. Still divided by 9 to the 2nd. So we did one little piece of simplifying. What's this answer going to look like then? Nathan, what's it going to look like? 9 to the 5th power, exactly. And we'll put a box around that. If I use the word evaluate, then I want you to figure out what 9 to the 5th is. Generally, 9 to the 5th, I'm not going to ask you to figure out 9 times 9 times 9 times 9 times 9. Wow, that would get big. If you're getting really large numbers on your test, think, maybe Mrs. Deegan didn't want me to go quite this large, okay? Here I have 1 over y squared times y to the 8th. Where is y to the 8th? Is it in the numerator or is it in the denominator? Talk to your neighbor for just a moment. Explain to your neighbor where you think it is. Oh, who's your neighbor? These 2 rows across, these 2 rows across. Kayla and Lucy together, Sarah talking to Jake, Ben talking to Taylor back there. And today, Hannah, you get your choice of front or back. So does Angela. She gets to talk to the girls in front of her today. Do we have a consensus as to what we think? Where is the y to the 8th? Is it in the numerator or is it in the denominator? What are you thinking here? Ben?
Numerator.
It's in the numerator. Good, good. So we're going to write, I'm going to put over 1. If you thought denominator, please notice, it doesn't have something over y to the 8th. It's y to the 8th. Think of that as over 1. Excuse me. So this is one big fraction up here. You see that multiplication dot? What's 1 times any number? 1 times any number is the number. So 1 times y to the 8th is y to the 8th. What's 1 times y to the 2nd? Y to the 2nd. So technically, I have y to the 8th over y to the 2nd. I have one big fraction up there. I multiply the numerators together, multiply the denominators together. I got y to the 8th over y to the 2nd. What should we do to their exponents? Subtract them. So what are we going to get, Jordan? Y to the 6th power. Now, do you need to rewrite it like I did in order to get there? Absolutely not. You could have looked at this and said, these 2 exponents, I just have to subtract them because one's in the numerator, the other one's in the denominator. They both have the same basis. It's all multiplication. And it's like canceling on fractions. You guys remember when you multiply fractions and you have 1/2 times 6 over 9 type of idea, and we cancel with the 6? We're doing that same idea. These 2 down here cancel with 2 y's up here. I'm left with y to the 6th power. Okay, so as long as one's in the denominator or one's in the numerator, I can go ahead and subtract their exponents. Okay, any questions there? Okay. All right, then we have another property, and this is the power of quotient property. And what this does is it takes a quotient inside the parentheses, and notice there's an exponent outside, and that exponent gets given to, multiplied by, each of the exponents inside. Remember, this is a to the 1st power, b to the 1st power, and 1 times m is m. So I have a to the m over b to the m. And again, I say b cannot be equal to 0. Why do I have b cannot be equal to 0? Who can remember why b cannot be equal to 0? Taylor? Because you can't divide by 0. What kind of an operation is it? What word do I use? Undefined operation. That's right, it's undefined to divide by 0. So what we're going to do is we're going to take a over b, quantity squared. How do we write that using this property? And how are we going to write that using this property? Think about what we just had up here. How are we going to write that using the property? Hey, Jordan.
A squared over b squared.
Over b squared. A squared over b squared. You got to give the 2 to each factor that's inside the parentheses. If they had a different exponent on them other than a 1, we'd be multiplying those exponents. We'll get to that in just a little bit. So right now, these have a 1 and a 1. And we know that 1 times 2 is 2. 1 times 2 is 2. That's why they get the exponent of 2 up there. Any trouble so far? Here I have negative 5 over y raised to the 3rd power. Is the negative being raised to the 3rd power? Yes or no? Is the negative being raised to the 3rd power, ladies and gentlemen? No, it is not. Think of this as a negative 1 times that fraction that we're going to have. So let's apply this 3 to the fraction. What's the fraction going to look like, first of all? Let's apply that 3 inside the fraction. What's it going to look like? I need some more participation here. Jake.
Negative 75 over 1.
Hold it, hold it. Apply the exponent. That's all I want you to do right now.
Negative 5 to... No.
It's not a negative.
5 to the 3rd power.
Thank you.
Over y to the 3rd.
Over y to the 3rd. Now that negative is just going to be sitting out here being friends, okay? It's just sitting out there as a negative 1. Now, I want you in your heads to figure out what is 5 to the 3rd. And unfortunately, it's not 75, by the way. So 5 to the 3rd.
Oh.
25 times, or excuse me, 5 times 5 is, class? 25. And 25 times 5 is 125. Over this y to the 3rd times that negative 1 makes it a negative 125. Okay? Be careful with that. This would be evaluated, and I would expect you to be able to do that kind of math. 5 to the 3rd power? Absolutely, without the use of a calculator. You guys can do 5 to the 3rd. No calculator in this chapter, by the way. Alrighty. For those of you who weren't here last week. Okay, no calculator on this chapter. Got to be able to do my quiz and my test and my homework without the use of a calculator. Okay, questions here so far? Jordan?
So if it just said right as an exponent, would you just stop, or would you still have to put negative 5?
Right using exponents would be this right here, okay, with that negative sign in red there. Okay, that's right using exponents. Evaluate, you have to figure out what 5 to the 3rd is, and you got to take it times the negative 1. Okay? Anybody else? Angela?
On the last slide.
Previous slide to this one?
Yeah. Would it, like, if we wanted to go farther on that, would the correct answer be AB?
No.
It's like 2.
No, because the bases are different, you can't cancel them. They stand for different numbers. So the final answer here is a squared over b squared. I can't do anything else until I find out what a and b are. Okay? Anybody else? Jordan? Okay. Let's go to this one. Now I'm starting to get some power to a power in there. Got x squared over 4y, all raised to the 2nd power. Why don't you take a moment, see what you can do with this one, talk to your neighbor a little bit, and then we'll get back together. I want you to think about this one. Let's talk about this one up here. I hear some of you talking to your partner, some of you aren't. Some of you are talking, I appreciate it. Whether you're confused or not, talking to your partner is going to be a good thing. Get some dialogue going about this math. With that x to the 2nd raised to the 2nd power, these two exponents have to be multiplied together because you've got a power to a power. So x to the 2nd raised to the 2nd is going to become x to the 4th. All right. Now, this 2 also gets applied to the 4 and to the y down here. What exponent's on the 4? What exponent's on the y right now? A 1. What's 1 times 2? 2. So we're going to have in the denominator, we're going to have 4 to the 2nd power and y to the 2nd power. Does that answer the question you guys were having?
Yeah, well, we were just wondering, like, what operation is that in between the 4 and y?
when two items are sitting next to each other with no operation, it's understood to be multiplication. So a number next to a variable, understood to be multiplied. Okay? When you were in 3rd, 4th, 5th, 6th grade, you would have had a multiplication dot or a little multiplication sign like an X. We don't do that anymore. We just, when two things are next to each other, they're understood to be multiplied. Okay? Rebecca.
I'm confused on when you know when to add and when to multiply.
You add the exponents when you have like bases that are being multiplied together. This is when I get to add them together, because this is 2x's times 3 more x's. So altogether I really have 5 x's, right? Mm-hmm. If I have x to the second raised to the 3rd power, then I get to multiply the exponents. I get x to the 6th, because this is x to the second 3 times. That's what the 3 says, is that I'm supposed to multiply x to the second 3 times, which is really 6 x's all being multiplied together, right? Mm-hmm. Okay, that's what you missed on Friday or on Thursday, whenever we talked about this. So make sure that you either watch the notes, look at PDF, or come in after school today and get more help from me in regards to this. This is kind of the nutshell here. If you see the same bases being multiplied, you have to add their exponents. If you have a power raised to a power, you need to multiply the exponents. When we have a power divided by a power, we have to subtract the exponents. Those kind of go together, don't they? Division and subtraction.
So you don't divide?
Here I'm dividing. I have a division bar up here, and if these were the same bases, Rebecca, I'd be subtracting their exponents. If they were the same bases. If I had next to the second down here, I'd subtract their exponents. It's not the same base though, is it? No. So I'm going to have to, in just a moment here, finish this up and have x to the 4th and my y to the 2nd. And class, what's 4 squared? This would be evaluating it. This is finishing it up all the way. Okay? I think on your homework I'll probably have to tell you, this section here is right using exponents, this section is simplified. Evaluate it all the way. Okay?
So how do you know how far to evaluate?
You keep if it says evaluate, you have to have all constants multiplied out. You can't be left with a constant raised to a power. And if you have any bases that are the same, like if I would have had an x up here and an x down here, I would have simplified that. But since I have no more variables that are the same up there, I can't do anything else to it. That makes sense, Colin? Okay. Anybody else? All right, try another one here. This gets us a little more difficult, doesn't it? 2s over 3t, all raised to the 3rd power, times t to the 5th, all over 16. Again, take some time to talk to your partner, please. The first thing that I want to do with this one is I want to write it using exponents by taking care of that property. How can we write this 2s over 3t all to the 3rd power? How can we write that using exponents, please? Okay, Ben, how's it going to look?
Over 3 to the 3rd, t to the 3rd.
Alrighty. Then it's times this lovely t to the 5th over 16. Now this is all multiplication, so technically it's one big fraction bar line there. It's all multiplication. Okay, no addition or subtraction down here. Okay, it's all multiplication. So now when I look at this, I go, I got a t to the 5th on top, and I have a t to the 3rd on the bottom. What are we going to do to their exponents? Jordan? Subtract. What is 5 minus 3, Jordan? So I'm going to write t to the 2nd in the numerator because, think about this. 3 of the t's on the bottom cancel with 3 of the t's on top. Doesn't that leave me 2 t's on the top? T times t, t squared. Okay. It's that whole canceling idea. But you can subtract 5 minus 3 gives me t to the second. How about s to the third? Are there any other s's? Ladies and gentlemen, any other s's? No. So we're just going to write s to the third on top. And let's see, what's 2 to the third? What's that equal to? 8. And what's 3 to the third? How much? 27 times the 16. Now, don't start multiplying 27 and 16 together. You're working too hard. Can you do any canceling? Is there anything in the numerator that could cancel with something in the denominator? Jordan? The 8. How many times does 8 go into 16? 2. So that's just like canceling with fractions, ladies and gentlemen. So now I've got my s to the third on top, my t squared, all over, got 27 times 2. What's 27 times 2? Nathan? 54. And so this is our answer, evaluated. We had to do a little bit of multiplication there. We could do some canceling. Rebecca?
So when you go through that s, do you keep the 8 with it?
I could write them in any order I wanted to, Rebecca. It's all just multiplication.
But like, do you carry the 8 with the s? I didn't know if you.
These two are not connected. Okay? I could write it t squared s cubed and the 8 on this side. Does that make sense?
Yeah, I guess. I don't know.
The 8 is being multiplied. This is all multiplication. 8 times s to the third times t squared,
Yeah.
all divided by 27 times 16.
Okay, so since it's on the top, you like just leave it?
Yep, as long as it's in the top, I'm just leaving it there. I can cancel it with something in the bottom. That's why I did the 8 and 16, just like a regular fraction. Okay? But I can't cancel with 27 because nothing has a 3 in it up above. That is a factor. Yes, there's a 3 exponent, but that's not a factor. Okay? Anybody else? Emily?
So like the 2 to the third, like the one with the green,
Yes.
that one, if like the 2 to the fifth is on the bottom and the 2 to the third was on top, would then the 2 to the second be on the bottom?
In the end, it would, and we're going to do that when we talk about negative exponents the next time we get together, Emily. That's why I made that comment. However you subtract them, your answer goes in the numerator. And if we end up with a negative exponent, we'll talk about how to deal to make that a positive exponent, which is how you commented. It's going to end up in the denominator.
Okay.
Okay? You're going to see some things on negative exponents. You're going to be able to work with them just fine. Okay? Anybody else? You guys are asking some great questions today. Thank you. Okay, here I have a problem for you. Let's apply the other things that we've been using so far to this one, please. Talk to your neighbor. Okay, up at the board we have 3a to the, so that now we have our power to our power corrected. We should have 3 cubed, a to the 12th, 5 cubed, b to the third. And when we're evaluating, that means we have to figure out what the constant is equal to. 3 cubed is 27, 5 cubed is 125, and we've got our a to the 12th over b to the third. That's all the further we can go. 27 and 125 have no factors in common. You know, 5 times 5 times 5, 3 times 3 times 3. There's nothing in common between those. A and B have nothing in common. So this is where we stop. We put a box around this answer so that Mrs. Deegan knows that's your final answer, and I can find it very quickly on your page, please. Okay. Any other questions there? One's on the board here. From what I was seeing before, it looked fine. I just had to correct this one. Okay, so now let's go on to this one. Okay, let's see what we can do with this one, please. Okay, what is up here? Jordan technically has the correct answer, so equals this here. Let's take a look at this. We've got power to a power, which gives us our 21, times the 1. You guys all know anything times 1 is the number, right? So x to the 21st times 1 is still x to the 21st. So Technically, we don't need the 1 there. And then we have y to the 7th power times the 3 times the x to the 8th. Okay? Well, the x to the 8th and the x to the 21st, you subtract those. That's how we get our x to the 13th. And when I write this, I always put my constant first, my variable second. That's what mathematicians do. Jordan was being a rebel there. She was writing her constant second, and that's okay. I would accept what Jordan has. I would also accept this that I've written up here. It doesn't matter. As long as there's not a subtraction or something going on there, the order doesn't make any difference. We usually write the constants first. The variables usually go in alphabetical order. So there's another thing for you. So, questions on this one? Then we have a little bit of math to do here. So I need you to be looking at this problem. We have a story problem here. It talks about the luminosity of a star is the total amount of energy emitted from the star per unit of time. And it talks about the order of magnitude. We didn't talk about the order of magnitude the other day. So order of magnitude, we need to talk about that. We got the time today. We're going to talk about order of magnitude today, especially for those of you who may have tried to look at some of the homework problems. I said if they have order of magnitude in, don't worry about it right now. But let's talk about order of magnitude so you have some idea of what this is. Order of magnitude is the power of 10 nearest to a quantity. It's the power of 10 nearest to a quantity. So you guys know 10 to the first power is 10. How about 10 to the second power? What is that? 100. And we have 10 to the third power is 1,000. How about 10 to the fourth power? 10,000. Now, if you're looking at that and going, how did they get those so quickly? How do we know what number each of those are equal to? If I said 10 to the 6th power, somebody could tell me what number right away. 10 to the 6th power. It's a million. How do some of you know it's a million right away? Jack?
Well, the power is the number of zeros after the 1.
Exactly. The power is the number of zeros after the 1. So when I'm looking at powers of 10, 10 to the first power is 10. 10 to the second power is 100. So how many zeros get put there? Well, what we are looking at is putting a number and finding the closest power of 10 that it is. For example, I have 91,000 species of insects in the United States. What power of 10 is closest to 91,000? So I'm thinking about 10 to the first power, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth. Which one of those numbers is closest to 91,000? What do you think, Rebecca?
10 to the third.
10 to the third. 10 to the third is what number, Rebecca? 1 with 1,000. It's 1 with 3 zeros after it. Do you think that that number is closer to 1,000 than it is to 10 to the second or 10 to the fourth? You think 10 to the fourth? What number is 10 to the fourth? 10,000. So you think that 91,000 is closer to 10,000?
No, 10 to the fifth.
Oh, what's 10 to the fifth?
100,000.
100,000. So you think 91,000 is closer to 100,000 than 10,000?
Yes.
I agree with you on that one. 10 to the fifth, or the number 100,000. So when we say, what is the order of magnitude for this number, 91,000, we say it's 10 to the fifth power. There are about, 10 to the fifth power species of insects in the United States. Do we have to have it exactly? Not for what we're going to be working with. 100,000, it's close enough.
Are the 3 dots just the symbol for?
The 3 dots are the symbol for therefore. That is mathematical symbol there for the word therefore. So power of 10 closest to 91,000 is 10 to the fifth or 100,000. Therefore, there are about 10 to the fifth species. You'll get to use that in geometry. Sorry, some of those old habits creep back into my writing. Therefore. So we're looking at what power of 10 is that number closest to? And Rebecca got it, 100,000. Okay, it's closer to 100,000 than it is to a million, than it is to 10,000. So here we have a problem. In the United States, in 2003, the U.S. Department of Agriculture collected data on about 10 to the third honeybee colonies. And there are about 10 to the fourth bees in an average colony during honey production season. How many bees were in the study? Well, both of these numbers are in order of magnitude. Are there exactly 10 to the third honeybee colonies? No. Are there exactly 10 to the fourth bees in every colony? No. It's close to that. I want you to talk to your partner and decide how many bees are there in this study. Okay, talk to your partner. See what you should do about the math here. Ladies, gentlemen, if I told you there were 2 honeybee colonies, and in every honeybee colony there were 12 bees, what would you do? There were 2 colonies, and in every colony there were 12 bees. How would you figure out how many colonies? 2 times 12? So 24 bees? Okay, I'm telling you that there are this many colonies, and there are this many bees in every colony. Talk to your partner and decide what you're going to do. Do I have a volunteer to tell me what they would do to come up with this? Nick.
I would add the
Tell me what problems to write down, sweetie.
10 to the third
10 to the third
times 10 to the fourth.
times 10 to the fourth. So what are you going to do to the exponents then, Nick? Add them together, which is 10 to the 7th power. So there are this many bees in the study. How many bees is that standard notation? 10 million bees. Okay, close. Close. Okay, so now I'm going to go back to this other problem that we were working with here about the luminosity of a star, where the order of magnitude of the luminosity of the sun is 10 to the 30 watts. It's really bright, isn't it? Kind of like looking at this light in my projector. The star of Canopus is one of the brightest stars in the sky. The order of magnitude for the luminosity of Canopus is 10 to the 26. How many times more luminous is the sun than Canopus? Hint, hint. It's a ratio I'm asking for. Therefore, you use division when you're talking about a ratio. Talk to your neighbor and see what to come up with here. How shall we write the problem? Before, when I asked Nick to write the problem, he gave me a multiplication problem. How are we going to write this one? Got any thoughts, Jack?
10 to the 30th over 10 to the 26th.
10 to the 30th over 10 to the 26th. 10 to the 30th is the sun. Canopus is the 26th. And we wanted to find out how many more times is the sun than Canopus. So we got to take the sun divided by Canopus. And what's that turn out to be, Jack? 10 to the 4th. 10 to the 4th times as luminous. Or what number is 10 to the 4th? 10,000. 10,000 times more watts. 10,000 times more watts. Pretty bright. I just think all the stars that you look out at night and you think, they're so dim out there. And they're really quite bright once you get out there. You have to do some division.